Good day all. Today in this session, we are going to learn about Unit 5 Electromagnetic Waves, Unit 6 Optics. That optics, they have given ray optics and wave optics separately, two chapters. That is chapter number 9 ray optics, chapter number 10 wave optics. See, in the electromagnetic waves, you have to concentrate the electromagnetic spectrum, all the values which they have given, the ranges, all those things you must know, right? And in ray optics, you have to concentrate on the diagrams, ray diagrams, lens formulae, lens maker's formula, power of lens, and it's very important, optical instruments separately they have given, like microscope, compound microscope, simple microscope, and telescope, that is astronomical telescope, that they have given refractive telescope and reflective telescope, the two types you must know. So regarding all those, the diagram, they will ask the diagrammatical questions and separately the subdivisions like numerical based on that. So these are all the things we will see that. Then in that 10th chapter, that is wave optics, Huygens principle is very important, the wave theory, and you must know about the diffraction and the interference, or they have given in this chapter. So the diffraction and the interference, we'll see how they have given the derivation of the single slit and the double slit experiment, and based on the numericals, all those things one by one, what are all they have asked repeatedly in the previous year question paper and the sample papers. Let us see in detail, students. Yes, students. Now we'll discuss about chapter 8 electromagnetic waves. That EM waves, you must know about the various regions of the wave spectrum. If you know about this, you will get definitely 2 to 3 marks will come from this region. That means the range of the wave spectrum. Gamma rays, it will be there in the wavelength range of 10 power minus 10, and the method of generating by the excitation of atomic nucleus. And X-rays, we have uses also, we'll see. X-rays, 10 power minus 12 to 10 power minus 7, that is by bombardment of the high atomic nucleus, right? Ultraviolet rays, that is in the range of 10 power minus 8 to 10 power minus 6. That is the method of generating the same way by excitation of the atoms, they are bombarding and getting it. So visible range of light, as we know that very well, 0.4 or 400 nanometer or 4 into 10 power minus 6 to 0.8 into 10 power minus 6. Excitation of atoms, and infrared waves 0.8 into 10 power minus 6 to 1 into 10 power minus 3. By vibrating of the molecules in the atom, we will generating the infrared waves. Microwaves, that we are getting 10 power minus 4, range of the wavelength is 10 power minus 4 to 10. Oscillating, that is also by the oscillator, by generating the oscillators we are getting it. And radio waves also, we can have the wavelength range of 10 power minus 1 to 10 power 6. By oscillating the LC circuit, we are generating the radio waves. Next we will see the uses also. So children, the question is, why are microwaves considered suitable for the radar system used in aircraft navigation? See, the microwaves, which are all short wavelength, the range, it has the short wavelength, so that only we are using in the radar system of the aircraft navigation, right? And the second question is, to which part of the electromagnetic spectrum does a wave of the frequency 3 into 10 power 13 hertz? So we can say that that is the infrared red. So the infrared red waves, or the frequency range of 3 into 10 power 13 hertz in the electromagnetic spectrum. So that only I said that tabular column of the ranges of the electromagnetic wave spectrum is very important. And arrange, next question is, arrange the following electromagnetic waves in order of increasing frequency. So they have given gamma rays and microwaves, infrared waves, and the ultraviolet rays. So increasing order, we can write that microwaves were less than infrared waves, IR waves. So both are same, right? And it is less than UV, ultraviolet. And which is less than gamma rays. Right? So this is the increasing order of the waves which they have given in the question. So we have arranged it. So next question, identify the types of waves which are produced by the following wave, the following wave, and write one of the application. So one application of each you have to write the use, right? You can write now the radioactive decay of the nucleus. First question they were asked about the radioactive decay of the nucleus, which is in the gamma ray. The gamma ray, which is used in the radioactive decay, and it helped to use for the treatment of cancer and the tumor, we can say. Okay, so the next one they have asked about the rapid acceleration and the deceleration of the electrons in aerials. That is, we can say the short range, that is the radio wave, and it is used in the radio treatment of, the television of and the communication system, in that they are used. The radio wave, that is the short range radio, television, and in general we can say the communication. Right. So the next one is they have given about the bombarding a metal target of or by high energy electron. By bombarding the metal target means we know that very well, that is the X-ray. And also it helps to study the crystallography or crystal growth. Right. So these are all that, if like that they have asked, you can get it. It maybe will come in the 3-mark question. Easily you can get the 3 marks. Like if you know, very confident with the wave, the EM wave and the range, how it is production, where and all we can use it, the ranges of wavelength, if you know, so it is very easy to get the marks from this chapter, students. The question is, an object is placed in front of convex lens made of glass. And how does the image distance vary if the refractive index of the medium is increased in such a way that still remain less than glass? So you must understand the question first, and you have to read the question once in a 2 time and 3 time. See, an object is placed in front of the convex lens made up of glass they have given. So you have to compare the range of the mu, right? So first the formula which you have to write 1 by F, which is equal to 1 by V minus 1 by U. And from this you can take that as comparing that 2 mediums, that is 1 by F, which is equal to mu I by mu M, 1 by F, which is equal to mu I by mu M minus 1 into, we can say that 1 by R1 minus 1 by R2. We can say that is the formula of lens makers, right? So we can say here, if suppose mu M, the mu M which is increases, which means what will happen? The mu I 1 by F value will be decrease. So that we can say that the V value will also increase. So this will be happening. How does the image distance varying? The image distance V is increasing, right? The next question is, A concave lens of refractive index they have given 1.5 is immersed in a medium of refractive index they have given 1.65. See the 1.5 of concave lens which is immersed in the medium of the refractive index of the 1.65. Then what is the nature of the lens? See, we can say the answer which is convex or converging. Okay, so convex lens or it is a converging lens. Because of the refractive index 1.5 is immersed in the medium of 1.65, it is less than this. By that way we can understand it is a converging lens, right? See the question, children. Write the necessary conditions for the phenomenon of total internal reflection to occur, and part of the question is write the relation between the refractive index and the critical angle for a given pair of optical medium. So the first part of the question is write the necessary condition for the phenomenon of the total internal reflection. We can say that the ray of light should be traveled from denser medium to rarer medium. The first point for A, we can say that the ray of light from denser medium, it must be from denser medium to rarer medium. Okay, it should be from D to R. Okay, so this is the first point, we can say that. And the second point is angle of incidence is more than angle of critical, incidence of critical, IC. I is more than IC, we can say that. So that is nothing but the incident ray, that is the angle of incidence should be more than the critical angle. The IC which is nothing but critical angle. Right. The B part of the question, write the relation between the refractive index and the critical angle of the given pair of optical medium. For that we can say that the refractive index which is nothing but mu which is equal to the relation with the critical angle sin IC. Mu which is equal to 1 by sin IC is the relation between the refractive index and the critical angle. Next question. A convex lens of focal length 25 cm is placed coaxially in contact with the concave lens of focal length 20 cm. And you must determine the power of the combination will be the system that will be maybe the converging or the diverging in nature. We have to determine it is a diverging or the converging. They have given the convex lens of focal length. So that for that we must know the power of convex. So P which is equal to 1 by a formula, so that 1 by 25 centimeters, so that 0.25 you will get 4 diopter. Okay, and for the concave, power of concave P which is equal to, you must know about the coaxially in contact with that, so that the minus of 1 by 0.20 which is equal to minus 5 diopter. And then you have to know about next one is the combination of lens P which is equal to P1 plus P2. So that we can write here the value, it will come 1 diopter, minus 1 diopter. From that you may understand the nature is divergent. Nature of the lens is divergent lens. Yes. Yes, the question is, which two of the following lenses, L1, L2 and L3, will you select as objective and eyepiece for constructing best possible for the telescope and the microscope? Also, you have to give reason to support your answer. See, they have given 3 different lenses, the power ranges and the aperture. See, they have given the lens L1 at the power of 6D and the aperture 1 centimeter. L2 power is 3 diopter, the aperture 8 centimeter. and L3 power, which is 10 diopter, and the aperture is 1 centimeter. So we can say that the telescope for the range of, we can take L2 is the objective and L1 is the eyepiece, right? So L2 range is objective. We can take it for the objective by seeing the power. 3 different power they have given, L1, L2 and L3 of power 6 diopter, 3 diopter and 10 diopter. By observing it, you can understand that the magnifying power will be larger for L2, we can take it, means that is objective for the telescope, and L3, which we can take it as eyepiece for telescope. So that for telescope, that is objective lens, we have taken the objective lens is L2 and the eyepiece which we have taken that is L3. Okay. So because of the magnifying power, we can say that the magnifying power is larger for that. So that we have taken for the telescope the objective lens L2 and eyepiece is L3. For microscope, we can say, observe the lenses and the power aperture. So for microscope, we can say that the L3, which is the objective, right, and L1 is eyepiece, because of the angular magnification is more. For short range of focal length also it has. So that we have taken for is here for microscope, L3 is objective. And L1 is eyepiece because of the angular magnification is more for the short range of focal length. For both, we can say that for both of objective and eyepiece, right? Yes, the question is, it has 2 subdivisions. Subdivision A, draw a ray diagram to show refraction of a ray of monochromatic light which is passing through a glass prism, and deduce the expression for the refractive index of the glass in terms of angle of prism and angle of minimum deviation. So this is the first part of the question. First we will explain it. See, you have to draw the ray diagram to show the refraction of the ray of monochromatic light which is passing through a glass prism. You have to draw like a prism, then the incident ray which is passing through one face of the prism, that is one face we have taken AB. So the incident ray pass from the rarer medium to denser medium. As we know that it will bend towards normal, right? From R to D it is moving. Then it is the extended ray which is the incident ray, and it is getting refracted from denser medium to rarer medium. Again it is getting refracted. Okay, so that you will get the emergent ray. This is emergent ray which is at S. So then we are seeing that here the quadrilateral, that is QMRN. A is the angle of prism. So this is the incident ray which is on one face. This is the emergent ray you will get from AC face, right? Now let us explain about the refractive index of the glass in terms of the angle of prism A and the minimum deviation, that is DM. Minimum deviation here we can explain it. The extended ray of the E and the extended ray of I which is meet on one place, no, that is minimum deviation, DM or sigma m, we can say that, right? From the diagram, you can get it MQR. See, MQR in this triangle part, you can take that I minus R1. See, the incident minus the R1 plus E minus R2, which is equal to sigma we can take, as we already explained that extended ray, right? So that from the triangle MQR, we will get I minus R1 plus E minus R2, which is equal to sigma. So that we can rearrange and say that I plus E minus of R1 plus R2, which is equal to sigma, right children? Yes? Now, from the triangle PQN, see PQN, from the triangle that you will get it R1 plus R2 plus QNR, which is equal to 180 degree. Okay, so that you will get that R1 plus R2 plus the angle QNR. This we can take it 180 degree. So that here we can write A plus Q and R. That means A, which is equal to R1 plus R2. So that A plus Q and R, which is equal to 180 degree. A here, as we know, R1 plus R2. So that from this derivation part, we will get I plus E minus A, which is equal to minimum deviation sigma. Got it, children? Now, minimum deviation means you have to take it I, which is equal to E. At that point of minimum deviation, the incident ray which is equal to emergent ray, and R1 which is equal to R2 will be come under R, because there is no change of angle or anything in R1 and R2, so that R will come, and sigma which is equal to sigma m at the point of minimum deviation, so that the I value which is equal to A plus D by 2. Right, from this we will get A plus D by 2 and R which is equal to A by 2. As we know that the mu refractive index of the medium, which is equal to, from the refraction, law of refraction, mu which is equal to sin I by sin R. By applying I value and R value, you will get mu which is equal to sin I. Instead of I, you can write A plus dm or sigma m by 2 whole divided by sin R, which is equal to sin A by 2. Got it? The relation between the minimum deviation, right? So the second part, explain briefly how the phenomenon of total internal reflection, which is used in the fiber optics. So in the fiber optics, nowadays we are having a good communication system of that, because of the fibers we are all using that. See, it has the two different medium that we can say. One, it has the medium refractive index which is low, n or low mu we can say that, and the inside which we are using, that is the high n, that is the refractive index of the medium. The two mediums which are using here in the fiber optics is core and cladding. Core and cladding, the two different materials which we are using, because of then only when you are sending the signal or the wave, which will not be going ahead from this range or from the medium to another medium, because of the total internal reflection which is occurring inside this medium. The range is high, this one is low, law of cladding, so that you will get the signal will be going in a good digital wave. Okay, and also we can say that the refractive index of the material of core, which is higher than cladding. Core mu is more, or we can say the range is high than cladding. Right, so that we can say that when a signal in the form of the light, which is directed into the optical in the form of light, which means it is directed into the optical fiber at an angle which is greater than the critical angle, that we can say that I which is equal to IC, right? I which is equal to IC, or we can say that it is greater than that. IC, which means what we said, IC which is equal to 90 degree, that is only the critical angle. More than the critical angle, if suppose it is reached, we will get it undergoes repeated total internal reflection which is along the length of the fiber, and then it's coming out of other end, almost it's negligible of the loss of intensity. So that only we are getting the good range of a good signal which is coming out. Okay. Yes, the question is, draw a labeled diagram showing the formation of a final image by a compound microscope at the least distance of distinct vision. The second part of the question is, the total magnification produced by a compound microscope is 20 and the magnification which is produced by a eyepiece is 5. Then the microscope is focused on a certain object. So the distance between the objective piece and the eyepiece is observed to be 14 centimeter. So if the least distance of distinct vision is 20 centimeter, then you have to calculate the focal length of the objective and the eyepiece. First, we can see the first part of the question, that is, draw a well-labeled diagram of showing the formation of the image of the compound microscope of at least distance of distinct vision. In our book, they have given LDDV method and as well as the normal adjustment method. Here, we are seeing the diagram of LDDV, that is least distance of distinct vision. See, actually, the compound microscope, which means we can say that it is an optical instrument which is used for observing highly magnified images of tiny objects. And the compound microscope, it has the two lenses, right? It has two lenses and it works in such a way that the image of the object from the first lens, it acts as the object for the other lens, lens 2. So then only we are getting the highly magnified image which is formed, right? So we must know here the magnifying power of the compound microscope is defined as the ratio of the angle which is subtended by the final image to the ratio of the angle which is subtended at the image of the object. So when the final image and the object are situated at the least distance of distinct vision. The second part of the question, the total magnification which is produced by the compound microscope is, they have given 20 centimeter and the certain object, the distance between the objective lens and the eyepiece is observed to be 14 centimeter they have given, and the magnification which is produced by eyepiece they have given, the magnification of eyepiece is 5 centimeter, right? So now we are going to know, if suppose the least distance of distinct vision which is 20 centimeter means we have to calculate for the FO and FE, that means the focal length of objective lens and the focal length of the eyepiece. First we can see for the focal length of the eyepiece, they have given M which is equal to what? Magnitude 20 centimeter, and ME magnification of the eyepiece is 5 centimeter, and the distance of the microscope for that magnification they have given D which is equal to 20 centimeter. The formula, as we know, that ME which is equal to D by UE, right? So that they have given ME value which is equal to what? Eyepiece of magnification 5 which is equal to D 20 whole divided by UE. By applying that, we will get the UE value is 4 centimeter. Here UE is what? 4 centimeter, but we have taken that minus 4 centimeter for that eyepiece. So VE which is equal to D, because of the D value which is nothing but the magnification which is produced by the compound microscope, that is only the image value VE, so that minus 20 centimeter. The formula which is for the focal length 1 by F which is equal to 1 by V minus 1 by U for eyepiece. By applying the value, by simplifying it, you will get the FE value which is equal to 5 centimeter, right? So this is for the focal length for eyepiece, and you will get M, that is magnification, which is equal to M0 into ME, right? Objective magnification of objective into magnification of eyepiece. We need MO, so that by remodulating this formula we will get M by ME. By applying this value, you will get 20 by 5, that is equal to 4 centimeter, right? 4 which is for the magnification of the objective. So V0 also we must know. So V0 which is equal to, they have given on the whole which is 14 centimeter, okay? On the whole they have given the distance of objective and the eyepiece is 14 centimeter. From that we got MO value, that is 4. So from that we will get 10 centimeter. So this part is over. The next part we will get focal length of the objective. That is also the formula M which is equal to what? V0 I by O, or we can write V by U. Here we have taken objective, so that minus of V naught by U naught. So we know the value for M naught, so that the M naught value you applied and V naught value, then here also we will get the U naught value, which is equal to minus 2.5 centimeter. Here children, you must know to apply the formula, so that you have to recollect the formula, then you can easily get the value. Then U naught, which is equal to minus 2.5 centimeter, right? So as we know that very well, now 1 by F naught, which is equal to length formula, is what? 1 by V naught minus 1 by U naught. In the same way, have you got for eyepiece? Here when you applied the value, you will get the F naught value, which is equal to 2 centimeter. See, 1 by F naught, which is equal to 1 by 10. Here the 10 value we got it, V naught value 1 by 10 minus 1 by U naught value is what? Minus 2.5. By simplifying the mathematical work, if you done it, means you will get 1 by F naught, which is equal to 1 by 2. So that F naught, which is equal to 2 centimeter. Yes. The question is, define the term wavefront. How is it different from a ray? The second part of the question, depict the shape of a wavefront in each following cases. 3 different cases they have given. First, let us see the first part of the question, define the term wavefront and how it is different from a ray. So, wavefront is the locus of all points in the medium at that same pace. So, that is nothing but wavefront. And how it is different from a ray? See, the ray at each point of the wavefront is normal to the wavefront. Ray is normal to wavefront. For example, this one is the wavefront we have taken. This is the normal to the ray. Ray is normal to wavefront. And the ray indicates the direction of the propagation of wave, while the wavefront is the surface of the constant pace. Did you understand? Now the second part of the question, depict the shape of the wavefront for each following cases. Case 1, light which is diverging from a point source. See the diagram 1. This is the point source. The light which has diverging from a point source. So you have to draw the diagram like this. And the second point, light emerging out of a convex lens when a point source which is placed at a focus. Point source which is focused, which is placed at a focus, you will get the light will be emerging out from the convex lens. So it will be emerging out in that way, the phase difference, right? And the third point, using the Huygens constructions of the secondary wavelet, you have to draw diagram showing the passage of the plane wavefront from a denser medium to rarer medium. So you can take it, this is one of the medium. So this is a second medium. The wavefront which is from the denser medium to rarer medium. So we have taken the incident ray which is from the denser medium to the rarer medium. Got it, children? So this is the diagram for the third case. By using Huygens constructions of the secondary wavelet, we got the diagram. The question is, in Young's double slit experiment, describe briefly how bright and the dark fringes are obtained on the screen kept in front of the double slit and hence obtain the expression for the fringe width 2. See the diagram. See the double slit S1 and S2 which is focused on the screen P. See the diagram on the screen, children. You can consider a double slit, that is the Young's double slit experiment for that. So with the slits at a distance we kept, it separated the distance D, we can take it, and separation slits and the screen, right? So now you may get the y1 value A sin omega t and y2 value that B sin omega t also we can take it. Here the point of the maxima, that is for the bright fringes, we can say that S2p minus S1p which is equal to n lambda, number of n lambda. So point of minima, that is for the dark fringes, the condition is S2p minus S1p which is equal to 2n plus 1 lambda by 2. So that finally we will get S2p whole square minus S1p whole square. We have to take it, the distance, we have to calculate the distance from the screen to this we have taken D. So the D square minus x plus small d by 2 whole square minus d square plus x minus d by 2 whole square. By simplifying this, we will get S2P minus S1P, which is equal to 2xd. We will get 2xd. So 2xd whole divided by SP, n number of values, so Sn, P plus S1P. So you will get 2xd by 2d. So you will get, by simplifying it, xt by d. And for the maxima and minima, we can get it xd by d, which is equal to n lambda. And for the minima, xd by d, which is equal to 2n plus 1 by 2 lambda. So these are the condition for the maxima and minima, bright fringes and the dark fringes we are getting. Yes, students. So far we have learnt from electromagnetic waves, ray optics, and from wave optics. So many problems we have achieved. So many questions we have achieved. So you can practice these types of questions, right? See the video and practice the questions well in your rough note. Thank you, students.